Hope you guys are having a good Thanksgiving today. Today, is a time where we all get to around together with loved ones and take a moment to thank for our life's blessings for all of us. Thanks for all those who are living. Those who are not living, we should always thank them for making our moment special. And yes, we should always make sure that we take all the moments in life granted because you never know what you have till it's gone. So hopefully you guys are having a good Thanksgiving and make sure it's a good one. Make sure it's something that makes you guys feel happy. I'm already feeling happy as is. I just ate food with my loved ones, special food. We ate some chicken, rice, and yeah, we're gonna visit relatives and all that, which is very very fun. So yeah, in this video, I just wanted to record this video on a special day. I just wanted to get one short video with Unit 3, just one more special simulator that was supposed to go over. So I wanted to get that out the way, so that way we can proceed to the next videos as followed. So yeah, so today we're just going to go over certain formulas. We're going to go over this special simulator that I wanted to go over, and it's regarding with Air Force Interactive. So this simulation that I want to go over is specifically discusses really how airfoil really works. We have elliptical foils, flat surfaces, rotating cylinders and balls, lift, drag. Everything is inputted in the simulator from NASA. Now, this simulator itself is from NASA, the Glenn Research Center, and we can see here that there are certain things that are within this system that we're seeing here. So let's take a look at this on. We can see here that we have Earth, Mars, water, constant density, specific air TMP, and specific density. So what is this really like these two graphs and monitors discussing? These simulators are really just discussing about the behavior of airfoil. We did like a 3-minute simulator review on this. I think it was like simulator 4 or 10 about this simulator. This simulator is very, very important regarding with how airfoil works. So I just wanted to give you guys a good explanation of what this really is. This is known as the Kuda-Jowoski analysis that discusses about the conformal mapping within how airfoils and cylinders work. So yeah, you can zoom in the airfoil and we can see here that notice that the streamline is going this way. It's going in one direction. It's going there. It's moving right now. If it's frozen, it stops. The geometry we can see here, when we zoom in here, we can see that this is a typical airfoil. So let's just go over this really. So the reference over here is there. We have the mean camber line and the chord line. There's an angle that's being represented between the airfoil and the reference point. And we have the flow. The flow is going in one direction. This is the streamline. As we're seeing, it's going on that direction. And it's moving consistently around this. Airfoil is not linear. In this case, it's more curved because, air is not, it's going around an object in this case. You can see this from a top view. You can see this from a side 3D view, and you can also see the find option of really how the airfoil is kind of being there. So you can see there's a span, chord, and there's a flow that's kind of being represented here. This is like a graph between chord and span relationship. Nothing is really shown in here right now because right now it's not really moving. So yeah. In here we can see that there's a flight and testing. We have over here Earth, Mars, and all these parameters I just showed you guys. Mars is a bit different. We can see that Mars is, it's just a different color at that point. But yeah, you can see that there's another graph. This is about the free stream. So we have press PSL and we have chord. So really we have, the relationship between both of these, the pressure and we have the chord line. You can always rescale it if you want. And this is kind of really what it is on Earth, Mars, water constant density. And we can see also specific air T density, TMP, which is I think air time and pressure. And we have specific density or viscosity that's also shown. And each time the speed, altitude, pressure, density in feet cubed, temperature, and viscosity, slug feet per second, are also shown within each of these parameters. So you can see that there is a slight change that occurs within all of these. The units are all, we usually measure this stuff in metrics or imperials. In this case, we do imperial metrics because that's what we do in physics. So you have flight, shape. You can also change the shape of the airfoil in this simulator. So within the simulator, let me just zoom in this really quick. You can change the airfoil into an airfoil, an ellipse. This is what an ellipse would look like. This is the free streamline of how it would look. Plate, which is kind of more so like a curve kind of shape, like an actual U shape. Cylinder. Notice that there's a big curve that occurs within the streamline. Well, not the streamline, when it's moving, air is kind of passing through this object. And the ball. The ball just goes parabolic because, the ball always has a parabola shape that kind of goes through within the air. And yeah, we have spin, the RPM. Radius for feet and span feet is just, the distance that we talked about between span and chord within an airfoil. We've talked about that as well within a previous video. There's also probe. You can measure velocity, pressure, and smoke within air. You measure velocity. Let's say it's not symmetric. This is symmetric. This is at 4.824 times 10 to the 0th miles per hour. We have high camber. This is the high camber line. This is the basic shape for that. I didn't test these parameters yet, but yeah, we're just like kind of going over shape. But now we're going over probe now. So we have velocity, 3.977 times 10 to the 0th miles per hour. And we can see that the curve is more so upwards than downwards. We have a flat plane. There is no airfoil. The airfoil is literally the yellow line over here. So we can see that it's a bit increasing as time goes on. Flat bottom. We also have negative camber. It's increasing. You can see that as we go on, the shapes increase. Once we change the shape, it increases afterwards. Then we have ellipse. And then we have the curve plate. Notice that the thick chords are all the same except the flat plate and the curve plate. And there is a very big difference within the camber to chord percent ratio. You can see that, from the camber percentage, not the ratio, just the camber line. You can see that, some of them are zeros, some of them are negatives, some of them are positive, and yeah, some of them, yeah. We also have gauges. Gauges inputs over here. We go over between lift and drag. So we can see if you go symmetric, it starts from 10 to the negative first. If you go to high camber, it increases a bit. Then it goes down, if you go to flat plate. You can see that the metric bar, this is just showing how much the lift and drag are kind of going in pounds. This is the scale to like 10 pounds approximately. So yeah, this is the flat bottom. Then we have, this is negative camber. And then we have the ellipse, then the curve plate. That's cool. So now let's just go over the size now of this bad boy. So yeah, when we talk about size for any kind of shape, let's go back to our symmetric airfoil. If you go to our size here, we have the chord, we have the span, we have the area square feet, and the aspect ratio that are shown here. So that's really cool. We also have our analysis as well. If it's stall, we can go over lift analysis. We can go over the Kuda-Jaworski condition within this thing. So I'm just going to go over really what Kuda-Jaworski is. Jaworski equation, because I haven't seen this equation actually. To also be very clear, I'm still also learning physics as well, so I'm just also kind of curious as well. So not with this one. Let's see. The theory for this is that the lift is related to the circulation of a bound vortex. Circulation of the bound vortex is determined by this, due to which the role of viscosity is implicitly incorporated through explicitly ignored. So it's just basically steady potential flow, so that potential airflow across a single airfoil related to like how the vortex is being circulated. So it's like basically air behavior that occurs, I believe, through a specific circulation of a vortex, and that's basically allows the air to flow around that single airfoil. So yeah, we have stall model for lift analysis. So yeah, we're going to go over all these now. So we have this lift analysis, we have the ideal flow. You can see here that we have the L to D ratio. I think this is the lift to drag ratio. This is the Reynolds. I don't know what that is. We're measuring this all in pounds. So yeah, bear with us. CUDA conditions, you can turn the CUDAs off or on. Let's keep it on. You can also turn the AR off, and you can turn the AR off if you want. You can change the ID off, the induced drag, and then the RE number direction. You can have a smooth ball, golf ball, or rough ball, depending on what kind of analysis you want to do regarding with any type of airfoil. You can use balls, airfoil, or wings to kind of use this simulator as a way to go through. We also have geometry. Geometry, we can see here that there's a lot of calculations that are being made here regarding with the volume, and we also have other. Let me just put that up really quick. Let's just go up. I think. Oh wait, cubic feet. Okay, wait. Let me just really quick. So yeah, this is just going over the parameters that occur to calculate volume for geometry. We have data. This is all the data that's being induced here. So here we go. So they kind of calculate for us really the camber, thickness, chord, span, surface area, angle of attack. They do this all through calculation through the simulator using GitHub, which is very, very cool. Coding is definitely very awesome for sure. You also have generation. Generation calculates the radius, x value, y value, and the amount of circulation that occurs. Selected spot, we have pressure, velocity, plane, thickness, which kind of shows really if anything's moving. Right now, nothing's moving right now. So I'm just showing you guys really what kind of the graph would show. Angle of attack, speed. Right now it's a bit of a curve as we can see here. This is symmetrical, I believe, right? Yeah, this is symmetrical, so for sure this is a symmetrical airfoil. Altitude is decreasing from lift to altitude. As altitude increases, lift exponentially decreases. The wing is linear, so as wing area square feet increases, the lift will increase, and so is the density. So you can do drags as well. You can also change these parameters as well. Coefficient of lift, coefficient of drag, drag or lift. You can do all of those. And you can do drag versus polar. You can calculate and make sure that this is the ratio between these things. So you can make any graph you want with this, and they will calculate everything for you, which is very, very amazing. So yeah, I just wanted to go over this, really what this really kind of helps go over. This goes over a lot of in-depth stuff. If you guys want to use this for research, or if you guys want to use airfoil in general to discover certain things, the decoded Jaworski simulator is really, really helpful. I just wanted to go over this really, really special. This is a special thing I just wanted to go over with you guys. And now that that's done, I just wanted to go over now one last thing. And that is regarding with some equations that we can use with these simulators. So let me just see if I can show you guys certain equations that I want to help you guys go over. So of course, when we talk about any simulator regarding with Jaworski equations and whatnot, Jaworski simulators, we're going to go over about like 5 different equations. Bear with me. So the very first equation is essentially the Bernoulli's equation. And I'm going to just write this down for you guys because we've gone over the Bernoulli equation just a bit. So the Bernoulli equation, it helps measure the amount of, what's the relationship between the air speed versus the pressure of air. And remember, it's typically an inverse relationship that occurs within the Bernoulli's equation. So how we calculate this is essentially P1. Let me just get my notes really quick for you guys, so that way it might be more easier for you guys to kind of see this. So I don't have to write everything on my trackpad. So let me just bear with me for 1 second. Because I'm going to write things on a trackpad. I'll just write this on a mouse for you guys. Okay. So we have P1 plus half PV1 square plus P G H1. Oh dear. Okay. Alright, so now we're going to equal this. Let me just see if I can drag this in here. Is equal to the P2 plus, oh gosh. It's been a while since we used the whiteboard, the handy dandy whiteboard, so don't worry, bear with me. Bear with me, Kenyans, and bear with me to the audience watching. PV2 square plus PGH2. So we have here pressure energy, which is the initial pressure energy, plus that by half times PVI square. This is kind of reminds us of the kinetic energy formula, where we're essentially doing half mv square, but instead of doing half mv square, we're incorporating the m instead of this is essentially now known to be as whatchamacallit. This is now replaced with pressure. Instead of mass now we're using pressure in this case. And we're multiplying this by the potential energy per unit per volume. And this guy over here, how this is being incorporated is essentially the potential energy formula. For those who don't know, it's equal to the mgh formula. Notice that in this case, we're seeing here that the m's are being replaced with pressure. So that's very, very cool. That's very cool. And this is the final value of, this is the final after value. So this is after things kind of happen. So this is after, really, once the circulation and the flow velocities all occur. That's kind of really what it is. So you can see in this diagram over here, let me just zoom into this diagram. We're going to go over all these diagrams, really. So bear with me. This diagram over here really goes in depth regarding with how velocity works here. So really in general, we're seeing that velocity goes in one direction, and it's known to be as Bernoulli's equation or Bernoulli's effect or Bernoulli's theorem, however you want to call it. It's the reduction in pressure which occurs when the fluid speed increases. So as the fast air essentially increases, we're seeing that there's a lower pressure gradient, and if there's a slower air that occurs, slow air speed, there's higher pressure gradient that occurs. You can see here that there's an increased fluid speed, and that decreases internal pressure. We can see that it's all going in one direction. So we can assume that because that's the case, the initial pressure energy will be greater than the final pressure energy, depending on what the fluid airspeed is. And you can calculate this through the volume and the energy once you use all the formulas to kind of find your answer. You have to set them equal to each other. That's really cool. Now I want to go over another equation for you guys to kind of take a look at. So another review regarding with another equation that's also incorporated with here is going to be this formula. Let me just erase this really quick for you guys. Oh no. Oh no. Okay, let me just okay. That's not supposed to happen. Okay. So yeah, okay. So if you guys want to take a photo, this is cool. And now, let's take a look at the other formula. The other formula I want to go over for you guys is the, let's see, I'm just thinking what I want to go over with you guys really quick. So it might be a bit easier. Let's go over drag force. Yes, this is drag force equation. So let's go over the drag force. We have the, FD, which is the drag force. This is essentially equal to the coefficient of drag, times that by the reference area, or the cross-sectional area, times that by pressure, times that by velocity square. This is the flow velocity. In that, remember the Bernoulli's equation, that flow velocity that occurs? That's kind of really where we're kind of getting the drag force coming from. And it's dividing by half. This is dividing by half here. So essentially, this is similar to Bernoulli's equation. The faster you go, the harder the air pushes back. And yeah, the faster you go, the harder the air is going to push back, because the more you're going faster, then air is not going to push you back, because that's like kind of saying that let's say for example, you're moving very fast, right? You're moving very fast. Something is going very fast. Let's say, I don't know, let's say we had some kind of diagram where we had a hoverboard. So, hoverboard that goes like really fast. Okay? And let's say there's like this dude that's kind of like on that air, that's kind of on this hoverboard, right? So he's on this hoverboard, and it's going at approximately the velocity of this is, let's say, I don't know, let's say it goes like, if it's a very fast hoverboard, I would say probably at best, latest technology and all that, let's say it's like 95 meters per second. Let's say air pressure is much less than this. Let me just see what the velocity of the air is in meters per second. Let's see here. So 343 meters per second is the speed of sound, right? So let's say it's 343 meters per second of the speed of sound, right? This is the air. Wait, this might not work then. Okay, let's give a different kind of example for this. Let's say we had the velocity was equal to, let's say, I don't know, 390 meters per second. Yeah, this thing is going fast. It's beating the air sound. So yeah, this cannot work because this is kind of like really kind of the example of really what drag force is. Drag force in this case is not going to stop this hoverboard. This hoverboard is going very, 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 very fast. And you can see here that if it goes this fast, right? Let's put some speed. Speed. This is kind of speed, you know what I mean? So the velocity is going in one direction. It's going 390 meters per second, and the air is like 343 because the air of sound, we're just doing this by the speed of sound. So it's going very fast. And you're going very fast. You're kind of counteracting air. And air is going in this direction. So if air is going in one direction and the hoverboard is going in this direction, then, the hoverboard is going to go faster. It's going to go approximately at around like 50 meters per second faster. So we can see here the idea is really that drag force is the faster you go, the harder the air pushes back. In this case, the air is not going to be able to push this hoverboard because it's going fast. So, yeah, this is kind of very, very interesting to kind of see. And yeah, so we're seeing here we have the coefficient of drag. We're multiplying this by the cross-sectional area, I believe, with the drag. So we're calculating the reference area. The reference area, I believe, between the air and the hoverboard in this case, and then we calculate, the air pressure times that by velocity squared, and then we're going to divide that by 2. The velocity is essentially, these guys, the flow velocity of how much air is being shown. Now let's go over another equation as well. I just want to go over another equation really quick. Some in-depth analysis we're going to go over now is this equation. This is the pressure drop equation I want to go over with you guys. This is known as the circulation equation. This is the swirl length equation. And this one, I don't know how to calculate this from my head. I don't know how to use this yet because I haven't learned this yet. So just bear with me if you guys are very curious about circulation. We can see here that though I can go over the how the circulation of the air is kind of being flown within this diagram here. So we're seeing pressure drop. We're seeing initial pressure and after pressure. We're seeing the forces going in one direction. We can see that the initial pressure minus the after pressure divided by the resistance is, the R. This is the uppercase R. This is just resistance to flow R. That will essentially give us the force. The volume flow rate, we have to the resistance to flow R. The L is the distance, and we're seeing that R, to find the flow rate, the flow of R, you're doing 8 times pi times the length of the cylinder, dividing that by pi R to the fourth. The R is the radius of the circle, of the inner circle of the inner diameter of the, the cylinder. So this is the equation, if you guys are curious. R equals this times that by v velocity times that by d L. This is some calculus stuff. So I don't know really how you can calculate this yet with this. But this is just, if you guys are curious, how circulation swirl length, how that is calculated, this is how it's calculated. So really, in general meanings and simple terms of really what this is, it's really how strong the swirl of air is around the wing. So if you guys go over the air, how the air is kind of operating under the airfoil, the more swirl there is, which is the R value, the R value is the swirl, okay? I don't know what this is, or what this is. This is, I know what this is, I don't know what this is, the symbol over here. But the L is the distance. D is, I think this is a derivative, if I'm not mistaken, and V is the velocity. This is essentially some symbol. But yeah, to calculate this is essentially the swirl. The more swirl that you have, the more lift that you can have in an airplane. That's the kind of the main concept for that equation. The next equation I want to show you guys is the equation of continuity. Now the equation of continuity in this case, it really, if the main idea really is that you're multiplying here the initial pressure, you're doing the area, multiplying that by the velocity equals the after stuff here as well. So you're seeing the mass flow rate at positions 1 versus position 2. It's not, sorry, not after or initial. This is just positions 1 or position 2. You can see that the velocity, in this case, the second one is going in one direction. For position 2, it's going in basically both directions. So you can see here that mass divided by the change of mass divided by the time, that will essentially equal this initial mass flow rate at position 1. This will equal to the mass flow rate at position 2. We're multiplying this formula over here. Let me see if I can zoom this in for you guys. This is kind of really how we're calculating for each of the individual flow rate pressures at specific positions. So in general, the main concept here is that if the area gets smaller, the area speeds up. If the area gets smaller, the air speeds up. So when you squeeze water, for example, from a hose, the area of the inside of the hose, when you squeeze it, it's going to go fast. The area is going to it's going to decrease because there's less space, and then afterwards, a lot of water is going to squirt out, and that means that more air is going to be flowed out afterwards. So that's kind of really what we're seeing here. If you're squeezing, let's say this is a hose, then the velocity, the mass inside is going to decrease the volume. So because density equals mass over volume. If the mass decreases, if the volume decreases, then the area decreases, the volume could decrease, and then that kind of stuff happens, and then these kind of the positions will obviously decrease. So yeah, this is also good to note here as well. The next equation I also want to show you guys now is, I think we might have only one equation left, if that's the case. Yes. Oh, this equation. This is the expression of a lift of a cylinder. Okay. So this is a very, very complicated equation here. So we'll just simplify this for you guys. Really, for those who are interested about airlifts and whatnot, this is kind of really what we're seeing. So do not worry about this. This is a lot of calculus that's kind of being incorporated here, but let's just go over really the main equation here. In general, just think of it like this: L prime equals P times that by the V infinity. Yes, infinity. I did not write that correctly. Infinity times that by t. Now, really, what is this? This is the very important equation that's used in the simulator. So we're trying to calculate essentially the lift per unit of wingspan. In this case, this is essentially they're saying here this is the lift on a cylinder. We're not doing that. We're calculating this is the Kudas-Jaworski's lift law equation. We're calculating the lift per unit of wingspan. So that's kind of the wingspan. So this is wingspan. Let me just write that down for you guys, so that way I don't have to. Yeah. So this is wingspan. P is pressure. T represents circulation. So if you calculate the swirl length with that very fancy equation that has been used with so much fancy calculation, so much derivative nonsense that we're using, you can calculate T. So T is essentially the circulation or swirl length. So you have to use this. You have to use the whatchamacallit, the circulation equation to find R. Then you put R to find T. The V infinity symbol is the free streamline airspeed. You're just finding velocity in this case. In this case, velocity is known to be just the free stream airspeed. So you just have to calculate that as well to find your wingspan. So wingspan. Oh gosh. Let me just okay. So this will calculate. Oh gosh. This is. Hold on. So yeah, we're calculating airspeed as well. So this is also something to also kind of consider. Now, in terms of this, we're seeing this is just simple, just basic math. In this case, well, it's not basic math because you're also going to do some advanced math in here to kind of find these calculations. But in general, this is essentially the lift of the wingspan is essentially equal to the density or pressure in this case, times that by speed, times that by swirl. This is how you would calculate for the lift in general for a wingspan using Kudas-Jaworski's lift law. So yeah. So really in general, these are kind of the main formulas that I wanted to show you guys in this video. So now I just want to give you guys, just some key concepts that you guys should, note. Just some key ideas that we kind of gone over, so that way, I don't leave you guys very confused of really what's going on, because I did the main goal in this video was to just go over some essential equations that were used within this video, that we use within the simulator as well, so that you guys have an idea of really what we're doing in this simulator. That simulator is very, very important. So I just wanted to show you guys really what that is in general. So let me just put this stuff in here for you guys. So just key ideas to note. Just to note is really, for example, fast air has low pressure. That's what we learned. That's a key takeaway I want to show you guys. Air moves faster in narrow or curved places. There's another thing to also kind of note, because we're seeing here that as the more speed occurs in narrow or curved places, we can see that the relationship between that with pressure goes lower as fluid airspeed increases. So that's a very key idea to also note here as well. Let me just write that down for you guys. Another key idea to also note here as well is that the more pressure under a wing, or more pressure is incorporated, you're going to have a very longer wingspan, or you're going to have more lift or more wingspan. From that fifth equation, if you calculate that with swirl, if there's more swirl as well, more pressure under the wing, you're going to have more swirl, you're going to have more circulation, because the lift or the wing, in general, the wingspan is going to increase. And that's applied because of more pressure under the wing. Another thing to also note here as well is that the air pushes back when you move. That's essentially drag. The speed of sound is around 343 meters per second, as you guys saw how I did that, through usage of Google. You can see that as the air pushes back when you move, the more that happens, that's drag. It's combating, the amount of speed that you're incorporating within your object. And if that's clashing with, air, yeah, drag is kind of combating that. And especially this is common in airplanes too. Another thing to note is that swirling air helps the wings fly, because the swirl will help determine how much wingspan you need and how much circulation of airflow will occur. And the last thing is lift equals air density. So lift equals air density times speed times swirl. These are just the main concepts I want you guys to note when it comes to these kind of things. some cool stuff here. I hope you guys found that very fun. Let me just just copy paste that really quick for you guys. Yeah, so these are some key ideas I wanted to show you guys within this video. So yeah, I hope you guys found this video very helpful regarding with circulations and really this specific lab in general. So yeah, again, happy Thanksgiving to all you guys. Thank you guys for those watching, and if you guys want, hope you guys see you in the next video. And yeah, take care guys, and happy Thanksgiving.